Every one of these robots needs wheels that spin fast. Forward, backward, full speed. Spin one side one way, the other side the other, and it turns on a dime. And none of it works by plugging a motor into your microcontroller. The thing that makes it work is a $2 chip on a little board called a DRV8833, a motor driver. It's the translator between your tiny 3.3 volt brain and a hungry high current motor. Welcome back to minirobo. Last episode, servos for joints. Today, the piece that lets you drive wheels. And honestly, the part most beginners skip, then wonder why their robot won't move or why they let the magic smoke out of the ESP32. By the end, you'll know what a motor driver is, the bare minimum to wire one up, where the tech came from, and the mistakes I made so you don't have to. Let's get into it. So here it is, a small breakout board with DRV883 chip in the middle. It's a dual motor driver, meaning one little board runs two DC motors. Perfect because most mini robots have two drive wheels. You'll also hear about its bigger cousin, the L298N. What does it actually do? Inside is something called an H-bridge. A plain motor wired straight to a battery only spins one way. An H-bridge is a clever switch arrangement that can flip the current direction on demand. So your motor goes forward and backward. And it can chop that power on and off thousands of times a second, so you can also control speed. Direction plus speed, that's a motor driver. Bare minimum to use it. Think of the board as having two sides. On one side, the motor power, your battery in and two motors out. Usually screw terminals or solder pads. On the other side, the control pins that go to your ESP32. The control side has 4 signal pins, AIN1, AIN2 for motor A, and BN1, BN2 for motor B. 2 pins per motor. And that pair sets the behavior. One high and one low spins one direction. Flip them the other direction. Both low is stop. Wire those 4 pins to 4 GPIOs on the ESP32, and you're good to go. Here's the key idea. The motor power comes from a battery, like a small battery pack, into the driver's power input, not the ESP32. The ESP32 only sends those little control signals, and, critical, connect the battery's ground, the driver's ground, and the ESP32's ground all together so everyone agrees on 0. To make it move, you set those pins from code, and to control speed, you send PWM. That same pulse trick from the servo episode. So instead of just on or off, you get 40%, 70%, full throttle. Hear that? That clack is how motors changed direction for a century. Built from relays exactly like this one, in industrial gear, factory machines, elevators, anything that needed a motor to run both ways. It worked. It was also big, hot, and expensive. The leap was cramming that whole H-bridge, plus protection circuits, onto a single integrated chip. For a long time, the famous hobby one was the L298N, capable but bulky, inefficient, and it wasted a lot of energy as heat with a big metal heatsink. Great for learning, not great for a tiny battery-powered robot. Then, chip makers like Texas Instrument among them, who makes the DRV8833, designed a new generation built on MOSFET switches instead of the older transistors. In plain terms, they waste far less power as heat, run cooler, and work down at low voltages tiny robots use. So you get this little board that's a fraction of the size of the old L298N, sips way less battery, and costs about $2. Same idea the industrial world ran on, clacking relays for a century, shrunk to a postage stamp and handed to us for a couple bucks. What I wish I knew. All right, the painful lessons. 1. The mistake everyone makes once, so let's make it on camera. Everything's wired, the code is right, and the robot is haunted. The reason? Battery ground, driver ground, and ESP32 ground aren't connected. So nobody agrees on what 0 volts means. If your build ever acts possessed, check the grounds before you check anything else. Burn this in. 2. Know your driver's limits. The DRV8833 is built for small motors, the kind in mini robots. If you bolt big beefy motors on it, they pull too much current, the chip overheats and shuts off or dies. Check your motor's current draw against the driver's rating. Small bot, DRV8833. Big, hungry motors, you need a bigger driver. 3. You'll wire everything up and one wheel spins the wrong way. Don't rewrite your code in a panic. Just swap the 2 wires for that motor, or flip which control pin is high in software. There's no correct polarity on a DC motor. Backwards just means swap. 30 seconds, done. 4. If your whole robot resets the instant the motors kick in, that's a brownout. The motors grab so much current that the voltage crashed for everyone. The fix? Solder a small 470 microfarad capacitor across the driver's DC in and ground. That little reservoir of charge soaks up the current spike so the rail doesn't sag the instant the motors kick in. Stable power is half of robotics. So that's the motor driver. A $2 H-bridge that stands between your delegate brain and your hungry motors. And finally, let your robot roll. 4 control pins, a battery on the motor side, shared grounds, and you're driving. This week's 60-second challenge. Find your motor's wake-up number. Lower the PWN value in code. 255, 150, 80, until the wheel only just starts to turn. And post the number in the comments. That's your motor's deadband. Below it, the driver hums and nothing moves. Every motor is different. Every slow driving robot you'll ever code starts from that number. And knowing yours is gold. The 4 pins, the ground rule, and all 4 lessons fit on one cheat sheet card, free on the episodes page at minirobo.io. But a driver needs something to drive, and we've been hinting at this the whole episode. Next time on Mini Robo, the motor itself, the AIN1 gear motor, the tiny powerhouse behind almost every mini robot on wheels. Subscribe so you don't miss it. All the parts are linked below, and post your first rolling robot in the comments. I love to see them. See you next time. Let's build something.